We're going to be joined this afternoon by Noor Rouafi, the project scientist of the Parker Solar Probe. Does that embarrass you a bit, or what? No.
I'm not going to talk about the probe.
If you twist his arm a lot, he'll talk about probe.
I have talks ready if you want to.
Maybe later. And he'll be talking about what polar perspective can bring to space weather research. And thanks for joining us.
Thank you. Thanks, Scott. So we got a healthy dose of polar fields of near-surface observation all morning long. This is the first talk that is dealing with space weather. And there are reasons for that. And in my personal view, a mission that have a chance of success should have a good, healthy space weather component. In particular, a mission that is going to see the sun out of the ecliptic. If we are missing that, probably we are missing a big component of solar and heliophysics. Why we need the out of ecliptic observation for space weather? Many reasons. I will give you just a few examples. These are a series of CMEs that occurred in 2014 in succession. The big one occurred on the 7th of January 2014, and it was a big CME, partial halo CME. And the Van Allen probes are operated from APL, and people there were so excited because they didn't see a big event. And they thought this is probably the event of the mission. And they were planning to reorientation maneuver of the spacecrafts. They have to delay that maneuver just to observe this event. But it was a big miss. And the reason at least at the beginning, we thought that the CME was directed toward Earth. It was a big miss because we didn't have the right perspective to characterize the direction of propagation of the CME. And more than that, the CME started at a very high velocity, more than 2,000 kilometers per second. When the flank hit Earth, it was just 500 kilometers per second. It was a very benign event. So there are other events. They occur, but we don't detect them. They are missed. And of course, we just feel them only when they reach Earth and they have some consequences. And we miss them again because we have just one viewing point, which is Earth or L1, and stereo helps a little bit, but anyway, it's still the ecliptic. To overcome all these limitations, it would be really greatly helpful if we get another viewing point out of the ecliptic at high latitudes. And this will provide many benefits. First of all, we can have stereoscopic observation of CMEs. We can constrain their velocities, their direction of propagation. We can follow their evolution as they are propagating in the heliosphere. We can detect other structures like co-rotating interaction regions. And as Sarah alluded to this morning, we can access the magnetic field, the BZ component of the magnetic field interrupting structures, which is really important for space weather forecasts and for geomagnetic activities. So let me go back. This is the type of orbits that are pretty interesting. Going out to Jupiter and coming back, that will give you a highly elliptic orbit. And you will end up observing part of the time. You cannot cover the whole orbit because the spacecraft will be far away at a certain point. But if we are within the orbit of Earth, let's say at 0.5 AU, like this movie shows, we will have a good chance of making really very key observations that can give us some breakthroughs in the physics of CMEs and space weather forecasts in general. So the type of open question that we can address is, I basically mentioned all of them, is mapping the heliosphere structures, measuring CMEs magnetic fields, determine the 3D structures and also the parameters mass, velocity, and their evolution as the CME is approaching Earth and the other planets. And we can really benefit greatly from those observations out of the ecliptic. Now, assuming that we have an observatory that is at near 1 AU, we have a spacecraft or 2 or 3 or 4 that are observing out of the ecliptic, we can address all these open questions here. How does shock propagate around the sun? And this is really important because recently we discovered whenever we have a big event, you see energetic particles almost all at all longitudes. It doesn't matter where the event erupts from. If you are on the other side of the sun, you will still see energetic particles. And this is really a big question, how these energetic particles are transported throughout the heliosphere. There are ideas out there that basically whenever you have a big shock, that shock spreads almost surrounds the sun and it injects particles. But this has to be confirmed. And again, if we are observing from above or from below, we can see where the structures are propagating, what direction, and we can actually decouple the CME from the shock itself, which is sometimes a little bit tricky doing it from the ecliptic and from Earth. There are also the question about sympathetic CMEs, the interplay between CMEs and shock waves and coronal holes, how CMEs interact between each other, the question about the origin of the solar wind. I talked about the decoupling of shocks and CMEs. The other thing also, it is really important to characterize the CME in terms of mass and velocity. And having just one viewing angle, in particular for helio-CMEs. For helio-CMEs, it's really problematic because we have so little, we can only get little information about velocity, about the propagation and evolution, and far less about the mass. If we have one event that is coming toward us, but we have also another viewing eye above, then we can have a better idea about that. There is another advantage for white light imaging in particular. We are always facing the F corona, which is the dust component of emission. And when we are sitting in the ecliptic, we are facing two things. First of all, the line of sight is so huge, and you get a large component, I mean, lots of scattering from dust. And the other thing also, the scattering geometry does not help. If we go above, that line of sight will be smaller. You will have less dust to deal with, and you also the scattering will help as well. So if this is the dashed line is the K corona, this line here is the F corona as observed from Earth, from the ecliptic. This line here is the F corona observed from 45 degrees above the ecliptic or below the ecliptic. It's much less than what is observed from Earth. So this is a big advantage if we can do that. We can do this. One more thing. If we go above, there is talk about asymmetries in the distribution of dust and things like that. If we go out of the ecliptic, that will help a lot to characterize the distribution of dust around the sun, which is really important. I can give you one example why it is important in particular. We have to deal for a number of years trying to model the dust distribution around the sun, in particular when we are so close, for solar probe. And it is still one open risk. That is probably the biggest risk we are facing, that we cannot close. Because if we get hit by a particle of dust, it can do some damage to the cooling system or something like that. But we did our best, but we cannot do more. If one of these missions goes out of the ecliptic and give us some additional constraints on the distribution of dust for future missions, that will be very beneficial. This is what Sarah mentioned this morning. What we see as transverse field from Earth, it will be line of sight from the North Pole or South Pole, and that's a straightforward measurement using Zeeman effect or some other, Faraday rotation. Hanley effect can be also very useful using some infrared lines. One of them is the helium 10830, which is very nice coronal line. Hopefully, DKIST will prove that this line is probably the best hope for us to measure the coronal field. It is so sensitive to weak fields, going from a fraction of Gauss to about a couple of Gauss, which is the strength of the magnetic field in the corona. This is irradiance prediction also. The advantage of being out of the ecliptic is that, and here I'm ahead of myself. For what I'm going to say now, one spacecraft would not be enough. We need more than one spacecraft. If we have full coverage of the sun, we will better characterize the irradiance, either spectral or total, or basically we cover the whole thing, and this is beneficial for the magnetic field for all type of observations. Well, this is what Paulette proposed some years ago, is to have a spacecraft in a near circular orbit at 0.5 AU, and using solar sails, and we have 42 kilograms for the payload. We have power. We have. I mean, she gave all the specs that are needed for this mission, and this is the instruments she proposed. They go from heliosseismology to magnetic field measurements to spectroscopy to irradiance, energetic particles. It's a pretty healthy payload. Now, I go back to what I said earlier. If we go just with one spacecraft, we will always have one limitation. We will cover one hemisphere at a time. We cannot do more. And ideally, we want really full coverage, because we are, since the space age, we are always suffering from observing one hemisphere. And look at models, for example. If you want to do global MHD models, they will rely always, at least partially, on old magnetic fields. This is very limiting. Solution to that, hopefully NASA will agree to it, is to have a constellation of spacecrafts. And what we need is 4 spacecrafts. Using the same orbit that I showed before, which is almost a circular orbit at less than 1 AU. And with this distribution of this spacecraft, we will have 4 pi coverage all the time. And there is one more advantage to this. All spacecraft will be seen from Earth all the time. We don't lose track of them. And this is probably one of the problem here is how to put them in orbit. And that's actually what we are doing at APL now. We got some internal funding, and we are looking at this very closely. If there is a way to inject this, I mean, to put these spacecraft at this orbit, near circular orbit, it will be good for us who are doing imaging, spectroscopy, and magnetic field measurements, but it will be also good for our friends who are doing heliosseismology. Because if you put a spacecraft on an elliptical orbit, it's not good for them. And this is the way for them to make reliable measurements from the poles to see what is going on inside the sun. So this is my summary. It's basically what I said throughout the talk. This is probably one of the best, if it happens, one of the best ideas out there. I mean, to provide the full coverage of the sun at all time. Thank you.
Any questions?
I expected orbits to be ellipses in a way, and that was just a crazy thing that I just saw on that screen. So what's going on with that? How does that work at all?
One of the ideas is to your solar sails. We have a couple of guys at APL. They are crazy enough, and they believe they can do it without solar sails. And it's... And what's that? Yeah. And basically, it helps to get the spacecraft out of the ecliptic. That's one of the ideas. There are some other ideas, but they are really in a preliminary stage.
And what's the estimated cost of that constellation? Not the, just pick a number.
Half a billion.
$500 million? Hold on, I've got a checkbook over there.
This is just, I picked the number, but this has to be looked at very, very closely.
Yeah. Lisa?
You may have mentioned it, maybe I missed it. So I know you said that it had to have the Jupiter assist. How long from launch till you could get into that kind of orbit? Like what kind of time frame? Are we looking at 15 years out before we can get there? Or is it 5 years out?
No. If it is 15 years, it's not worth trying.
Okay.
It should be shorter than that.
So how long from launch to?
We have really to look at these orbits, and that's actually why we got this funding at APL to look at how to get the spacecraft in those orbits. But if it is more than 2 years, I would say it's too long.
More than 2 years, you think is too long? Okay.
Yeah, I think also mass is going to be pretty challenging. But thank you again, Noor. We'll bring this back up when we get to discussions later. Yeah, so there's a constellation. 4-pi measurements. I think we've heard a mix today of people wanting global coverage and making sure you have global coverage, all longitudes and latitudes. But that means that if you're going to build something, you need to build something that's highly reproducible, keep the cost down. But there are other strategies, right? You could put different instrumentation on each bird and do it that way too, if you kind of oversample.
Is it this way?
So,
left, right?
There's a lot of trade space here. But things are heading in the right direction. So, Heather, you ready?
This is left, right?
I don't know.
Correct? Left, correct.
Okay.
What?
Does this?
No idea.
I'm not sure that that works. Okay. I think you may All right. All right. No problem.
So now, second talk, Heather Elliott from Southwest Research will be talking about understanding the origin and acceleration of the fast solar wind and the need for new observations. So please take it away.
Okay. I'm happy to be here. I found the work that I have done on Ulysses to be very interesting, and it's very applicable here. I'm going to jump in, go ahead, and show some examples of Ulysses. So one thing that Ulysses did do was give us an idea about the 3D structure and how it changes over the solar cycle. But in addition to that, and this has been latched on, and the simulations can reproduce some of these large-scale features. But Ulysses data, and even some of the data in the ecliptic, have revealed information, revealed features that I don't think are currently explained. And some key things to point out is that the polar coronal holes do change in size over the solar cycle. I think Karen Harvey published a nice paper on that. And you see that the inward polarity hole at solar maximum is much smaller than what observed at solar minimum. But there's a whole evolution of the coronal holes. All right. So this is a plot that shows the solar wind speed as a function of latitude. And the black curve was at solar minimum. And as we go across the poles, we see a change in the solar wind speed by a small amount as a function of latitude. And then eventually when you get to around 20, then the speeds drop. And so this is a pointer. Yeah, okay. In here, we're going in and out of the edge of the polar coronal hole. And then these, this is probably the same coronal hole, but it's the edge, and so the speed drops off, and these could be different coronal holes here. The orange curve is a scan from solar maximum, and you see that the tops of the peaks of the coronal holes match the same kind of profile. The peak speed kind of drops off with the same latitude trend. I've never seen anyone explain that. Okay. In order to show some plots later on, I want to explain what I've done with some of the ecliptic observations. This plot, this bottom plot, shows just solar wind speed as a function of time, but I've color-coded the rises. I set a threshold. If it rises more steeply than this given criteria, I color-code it orange. And if it's falling less than that steepness, it's color-coded blue for rarefactions. So in orange are the compressions and the refractions, but identifying them by the rise and the fall. And so superpose epoch analysis of co-rotating interaction regions where the fast wind is running into slow wind that was emitted earlier in time shows that when you have this rise in speed, which is the blue curve, it's keying off of a stream interface for all the different CIRs. You get slightly in front of it, you get compression, and you get the density enhancement, and you also get enhancement in the magnetic field strength. And then you get a rise in the temperature here, and then just inside the coronal hole, like you're in the coronal hole over here, you have an elevated temperature because the coronal holes have a high proton. This is like proton temperature here. You don't necessarily see a significant change on average in the alpha ratio. But this is a standard effect that you see owing to what happens en route. And so it's important to know not only the properties of the sun, but also what happens en route. Okay, and so this dynamic interaction can even happen over the poles over the poles. And so this is a plot as a function of time. I have on here the distance and the latitude. And I've done the same type color coding. And you see when we're skirting the edge of the polar coronal hole, you have these really intense CIRs here, where we're going in and out of the edge. And then in the polar coronal hole itself, we see little tiny compressions and rarefactions. And here I used a pretty hefty steepness requirement here, which mostly I was identifying the CIRs with that, but I even noticed that you can still see structures in here. And to look at that a little more, if I zoomed in on a smaller amount of time, and I'm also showing the proton temperature in black and the density in R, taking out the spherical expansion, just have scaled it there because I'm traveling a large distance here. But I've reduced the steepness requirement, and you can really see these rises and falls. And if you look at how they do the sorting of all the data from the polar coronal holes, taking all of them together, doing the same sorting, and then doing distance bends, bending the compressions and rarefactions identified by the steepness separately, what you find out is even over the poles, as we move away, these speed differences, as you move further away, you get you get enhanced densities in the compressions in the rises, and you get enhanced temperature in the rises, and in the rarefactions, you get a lower density and a lower temperature that evolves with distance. And so these small speed differences that are set up close to the sun, as you move further away, by the time you get to 5, where the Ulysses observations go out to about 5.4, you've got a really clean type compression and signature with density enhancements and pressure enhancements and field strength enhancements that develop. So it's really important to know these speed differences, these small speed differences close to the sun, and how they develop all the way from the sun through the corona and out to where you measure them in situ. Okay, so another interesting thing is that this is a paper from McComas et al. That we did with Rudy von Steiger, looking at Swix freeze-in temperatures that are estimated based on the charge state ratio, density ratios of the solid points are carbon 6 to 7, based off of carbon 6 to 7, and then the open ones are oxygen 7 to 6 ratio. And when you get to the edge of the coronal hole, this was an average over nine events, you see that the freeze-in temperature rises as you're going out of the coronal hole in this edge. So this was one idea where there could be happening something on the edge. And it's believed that these charge state ratios are frozen in or locked in the corona. Okay, so this is also a similar study here where they're thinking that, okay, you have fast wind, you have slow wind, and you have a boundary region. And here they've got elemental abundances for all of the iron charge states, and divided by the density of that divided by the ones for oxygen, and it's showing versus speed. And so these are the coronal holes here, and at this intermediate speeds you see a similar elemental abundance, but you see a major trend in the charge state ratios. And the elemental abundances are thought to be set down in the chromosphere, but the charge state ratios are believed to be set up in the corona. And then this one is the oxygen. So both in the oxygen and the carbon, we see a significant trend across this boundary. So my question is, it's not necessarily a boundary region all the way down at the surface of the sun. Where does it happen? And in order to do that, we're going to have to connect the solar observations to the in situ observations. Now, these polar coronal holes are also important in that they can have these long extensions. And this is a time period in 2003 where this extension was very long-lived. And you can see it developed. I have the dates here. And so, you know, within half a rotation, it's developed significantly. And this is from ACE data, and it's in the ecliptic near Earth. And the speeds are color-coded, blue for inward and red for outward field. And the solar coronal hole maps are color-coded the same way. And you see that the extension here is really fast, and it's moving at speeds above what you would expect. This was the trend from Ulysses of the polar coronal hole that I showed earlier. So it's moving at speeds that you would expect for a polar coronal hole right over the middle of the polar cap. But it's extending down to low latitudes and observed at ACE. And now the hole on the other side that is more disconnected and it tends to be smaller has lesser speeds. But what I noticed is I took the data and applied temperature versus speed. This is what you get. You see like there could be a branch there. And so I just took all the temperature and speed measurements for this time period and sorted for the whole year actually, and sorted by sector. And you see this outward polar coronal hole, which is really large, and we had a lot of data points in it, shows up really nicely. And so I just drew a box around it and I fit it. And I put the same box over here. And here, it's the same kind of time series for speed, but I've correlated whether it's in the box or out of the box, pink if it's in the box and outward polarity, and purple if it's in the box and inward polarity. And what you see is that even the tips of these polar coronal holes can follow a similar trend. Like you see, there's some there that's inward. And so my question is are the centers of coronal hole, like it looks like even the small coronal holes can have a center that's similar to a polar coronal hole, but adjusted for a different latitude maybe. And in addition, this is the same kind of 2003 time period. Here I've color-coded the compressions and rarefactions, and then showing some elemental abundances and some charge state ratios. And you see that across these polar coronal holes, the elemental abundances tend to be pretty flat and wider. And you see the regions where in the center of the coronal holes, like this one, where the charge state ratios are more uniform, is narrower. And the edge, you have these nice boundary effects, and it's repeatable. It happens a lot, especially for these really fast ones. So this brings up the concept, do you have these boundary effects here And are the small coronal holes, do they just have like a similar core, but it's just not as big, it's mostly boundary type? Or are just the small ones just totally different than the large ones? And here I've put whether it's in that given temperature speed box, and I've lined up for just mostly this one here, the compressions and rarefactions, and the elemental abundance ratios when it's flat, and when the charge state ratios are flat, and identifying these automatically by looking at how flat it is here. These are all automatically identified by setting various thresholds, because I want to look and line up and see how repeatable this is and for different size coronal holes. And so there are solar observations that look at outflow and how it lines up with the chromospheric network. And here, this is for quiet sun taken here, and this includes the polar cap and its boundary. And you do see some change across here. And then this one shows this coronal hole here, and quite a difference from here to here. And then also in the outflow character, it's different across here. So this is even kind of counter to the idea of a core. This is like like one side and another side. So I think there's a lot of work to be done on that. And kind of the overall big picture is to understand the details of the solar wind from polar coronal holes and their boundaries. We need comprehensive in situ measurements combined with remote measurements over a variety of emission lines to really look at the sources. And we need coronagraphs capable of precise tracking of small speed differences and small density differences through the low corona, so that we can compare the solar observations to the in situ observations better with the coronagraphs. And I feel like we need a mission that has a high latitude in situ observations and mid latitudes at the same time, so we can look at in situ observations at mid latitudes simultaneously with the core of the coronal holes. And if you're going to have multiple spacecraft, you really need to have smaller instruments so that you have a chance of being able to launch multiple spacecraft.
My job is never done. I get to multitask. Any questions? Yes, Don. Hold on. Coming.
Uh-huh. Yeah, I think matching the charge state ratio with what's really happening in the corona, if you can get temperature measurements at different heights in the corona, and also the elemental abundances, because that will actually allow you to really make the direct connection with the source. And I mean, I think that's critical. But the solar wind speeds and understanding those and how similar the extensions are to the centers of the coronal holes has implications for space weather, because those low latitude extensions are highly geoeffective. And yeah. Yeah, but there's this latitude trend that's not well understood. And I don't know, is it tied to the overall circulation in the sun? And then how well do things line up with the chromospheric network? Because through the elemental abundances, we do see changes at boundaries. And so I mean, I think those are open questions, and I think we do have the capabilities to go and actually do this. This is not, we need to make the instruments a little smaller so we can afford to launch it. But yeah.
Is that back to Hubal and Wu with network elements leaking all the way out and being sensed, every 20
Yeah,
megameters
well,
or so in scale.
and there has been more work recently looking at different emission lines, even more recently than what you and Scott did. That people are looking at the outflows and other emission lines, and maybe we can learn more about the profile. But even the chronograph tracking with the small, these are really small speed differences, and that actually would be pushing instrumentation limits for that one. But the in situ elemental abundances, and I think even some of the emission line stuff and trying to get temperatures out, I think that's just well within the capabilities.
Cool. Any other comments or questions for Heather? Well, if not, thank you very much, Heather. Ready? Yeah, composition. Awesome to have images looking down on it and be able to sense it as it's coming right down at you, or coming right out at you. As Heather pointed out, I think you're looking at, in some sense, you're looking at the DNA, or how that, both the origins of that material as it's come out of the atmosphere, and then what process produced it also. So in the fast solar wind, are you just seeing the signature of the heating process lower in the atmosphere versus what's coming out from the slow wind, which is taking some unknown amount of time to percolate out through the closed field regions? Seems to me that a polar observatory with composition could definitively answer that question. Or not.
Happy to introduce Chip Manchester. Yay.
There we go.
Who will be talking about polar observations impacts for coronal and solar wind modeling.
Thank you. The talk is going, I have co-authors here, Paul Van der Hulst, who's one of the primary developers of the model, in particular the two-temperature model I'll be showing, and Meng Jin, who's a student of mine who graduated about 4 years ago now, and is at Lockheed Martin. So I'm going to be discussing how these high-latitude polar observations can affect the modeling that we're doing, particularly as input for the model. The synoptic magnetograms that we use are highly impacted by observations. If we could get them at the pole, it'd be a huge improvement for what we could do. And then considering two sources of observations, primarily heliospheric imagers, chronograph observations made at high latitude over the poles, and how they would perceive the solar wind, coronal structures, and also coronal mass ejections, and how those three-dimensional views could give us, how those views could give us three-dimensional density structure from tomography, as well as even from looking at a CME from a different perspective, can radically change how we can determine the density structure. And then the second part of the talk, I'll be going over in situ observations, aspects of the modeling that we can do and how it would relate to observations in the solar wind, looking at turbulent energy density, wave dissipation rates, and very similar to the previous talk, looking at charge state composition. And then finally looking at temperature anisotropies, particularly the parallel and perpendicular proton temperatures, and these vary radically as a function of latitude, and vary a great deal going into the fast speed wind and the large coronal holes. So this is the nature of the model. I'll just go over this very quickly, that we're using an Alfvén wave-driven model with forward and counter-propagating waves. They propagate along the magnetic field lines. They dissipate along as a result of turbulent dissipation, which heats the plasma. So the plasma is being accelerated both by Alfvén wave pressure gradients as well as thermal pressure. We have different mechanisms for how that energy can be transitioned both to the electrons and protons. So there's a whole different forms of physics that we can prescribe for how that energy is partitioned between parallel and perpendicular proton temperatures, as well as how it heats the electrons. And we can limit those temperature ratios based on various kinetic instabilities, which are incorporated into the model. So this just gives the basic features of the model and what the model can predict and how this will relate to these observations. So this is where the model begins. Any model driven by observations, global model, begins with a synoptic map. And so this is one that was used for our model. This is a HMI, which has been, you can see the effect of the poles. So once we get to the poles, we basically have confidence in the observations at relatively, up to relatively high latitudes. But once we go over 60 to 70 degrees, there's a lot of uncertainty, especially in the last 10 degrees. And so the data gets smoothed out into these bands, into these polar bands. And typically, anytime we use data to drive the model, we have an issue with using some sort of a polar-filled synoptic magnetogram, because the data here otherwise is just simply too noisy, has too much structure, or too much noise, and there are just not enough data. And so we get a lot of variations, unphysical aspects of this that we just can tell does not produce a well-behaved coronal model. So we end up, in one form or another, of having to modify the data in the poles, or to use a polar-filled data in order to be able to get good results. So once we can get that data, we can begin to do these coronal models. And one of the things we'd like to look at is the three-dimensional density structure. So typically that's arrived at by rotational tomography done with the chronograph observations. So it's giving those line-of-sight observations that are integrating the brightness along these lines which are transparent, which are integrating light from Thomson scattering from the free electrons. So this is a movie of such a reconstruction. Well, I guess the movie won't play, but that's not necessary. So this is showing different isosurfaces of the densities. So the blue is at 10 to the 6 electrons per cubic centimeter, and the red is at 5 times 10 to the 5. And so we can, from that tomography, we can determine the three-dimensional structure of the electron distribution and relate that to the magnetic field. So you can see where these high-density regions tend to form at low latitude in the streamer belt and in the closed field line regions, and you can see the effect of the coronal holes at low and high latitude. So one of the things that the polar view would provide with some sort of chronograph observations is many more additional lines of sight with which to do this tomography. And so with that, you can do the tomography over a shorter period of time and reduce one of the artifacts that occur as a result of time variation in the solar wind. The second thing, of course, that the polar view provides is much more information about the streamer structure as seen from above. So you can see these stream interaction regions and these compression regions. The left is showing the solar wind speed on the equatorial plane. On the right is showing the proton density and showing clearly where there are dense regions where the compressions are occurring, where high-speed streams are compressing, interacting, and slamming into those slow-speed streams. So you get strong variation in that density as a function of longitude, which is something that could be much more readily discerned from a polar perspective. So the next thing we're going to consider are the coronal mass ejections themselves and that density structure and how that might be observed from high latitude, why that's important. So this is an observation by Meng Jin, 2017, for a CME that occurred in March 2011 from active region 11164. And so from the observations that it's occurring off the limb, it's a high-speed CME, and we model it with a Gibson low flux rope, which is shown here from two different perspectives. And this is showing the density structure within the solar wind compared to the ambient structure. So the density is enhanced at the base of the flux rope by a factor of more than 50, basically representing filament material, the cavity in the upper portion of the flux rope. And this erupts outward, simulating the CME. And so these are the observations of that event from the top, left, and right. I'm just going to show you. So this is showing a still frame, the LASCO C2 observations. Again, it's occurring off the limb, so you don't actually begin to see the CME until several minutes after the eruption. And this is showing the density structure at 8 minutes. The bottom is showing the simulated event from the Earth perspective, is shown on the left, and the polar view is shown on the right. And so you get a sense of how much difference there is in that perspective from these synthetic Thomson scattered white light images. we now go to a period of time at 60 minutes. This is showing LASCO C3 observations of this same event, the simulated event from an Earth perspective and the polar perspective. What really stands out is from the polar perspective is you now really see a large cavity within the CME that you don't see from the Earth's point of view. So you really begin to lose out on this three-dimensional structure when you only have a single point of view from an integrated white line image. So if we compare that to a three-dimensional image of the CME, from the simulated CME, you begin to see where that cavity occurs and why it's being missed. So this is being shown from two cut planes going through the center of the CME. The magnetic field line is shown here, colored with velocity. On the cut planes, the particle density is shown multiplied by a factor of r squared to flatten out the natural fall off with distance. And from a perspective of the Earth, you pretty much completely fail to see this cavity. There's enough additional material in front and behind from the perspective of the Earth that you miss this cavity, but seen from the poles, the cavity stands out very strongly. So again, you get a much better idea of what the true density structures of a coronal mass ejection by having these multiple points of view. The next thing that's very interesting the model provides is a temperature structure which varies greatly with latitude. So the model provides not only the perpendicular, parallel, and electron temperatures, and going especially from the perspective of the proton temperature, there's a tremendous variation in latitude. So that the poles are actually much hotter than the low latitude solar wind for the electron temperature. So this is a scale going up to 5 times 10 to the 6 degrees. So if you go to the electron temperature now, the temperature only goes up to 3 million degrees, but most of that heating is at low latitude, and you have relatively cool regions over the poles. And on the right here is the electron heating, which is even lower. And so the heating rates are shown in the bottom frames from left, middle, and right are the proton temperature heating fraction up to 92%, the parallel heat, proton heating up to 40%, and the electron heating up to about up to 10%. And so most of that electron heating is occurring primarily at the equatorial regions in close proximity to the heliospheric current sheet. So with a polar perspective, orbiting, taking in situ observations, it'll be possible to directly sample the solar wind and these temperature structures, in particular the temperature anisotropies, as a function of latitude. The next thing that the model can provide is the wave energy density. So they're showing observations, in situ observations at near solar minimum. The wave energy density is observed is shown in these black lines. The model energy density is shown in red, and then the velocity and magnetic field strength are shown in blue and green respectively. And the model actually does an extremely good job of reproducing the wave energy density that's directly observed from in situ observations at 1AU with stereo A, and then going through the compression region, you find a strong increase in that energy density as well, of course, with the velocity and the density. So again, these are features that could be measured as a function of latitude, showing where that wave energy density is highest and what the dissipation process is. And finally, in comparison with the previous talk, I'm showing here the charge state composition as a function of latitude. This is from Rona et al. 2015. The image here on the left is showing Ulysses observations of the charge state ratio of carbon 6 plus to 5 plus. The smooth densities are shown as a fact in red. The comparison, the simulated value here are shown on the right on the same scale, showing a very strong variation in latitude with the charge state composition. So basically showing a strong difference, a very strong difference in the temperature structure of these large-scale coronal holes found over the poles and how much that varies with the low-latitude solar wind. And on the right here, bottom is showing the observed velocity as well as the model results shown in red. So we can reproduce this type of structure. And what's important to this is being able to model the electron temperature, which is what's directly responsible for the ionization of these ions. The model is capable of that with this three-temperature structure. We can simulate the charge state and then compare this to observations and identify the thermodynamic structure over the poles. So to summarize, we can model the steady-state solar wind, stream interactions, and CMEs The AWESOME model provides a way of modeling not only the density structures, but also the wave, alpha wave density, which is driving the solar wind, as well as the temperature structure, temperature anisotropies, and then also being able to simulate the turbulent dissipation processes, all as a function of latitude, which shows strong variations. Hopefully, high latitude observations, magnetogram observations, would provide much more accurate input in the form of synoptic maps, which would have much more accurate magnetic field observations, which is particularly important because that region over the poles is the source of the fast wind that fills most of the heliosphere. So that's really critical, is to get the improved observations. With that, we can begin to simulate the solar wind, the stream interaction regions, and CMEs. And these high latitude observations are essential for giving us the three-dimensional structure of the solar wind, as well as the coronal mass ejections. We've also shown that there's a strong variation in latitude with the alpha wave energy density, which we have as a function in our model, which is driving the solar wind. This can be observed and compared to the model, as well as the temperature structure, the temperature anisotropies, and how those vary with latitude, and how that also can be related to wave energy dissipation processes. The most important thing, as we've already shown with the model, is that there are very significant variations of the high latitude wind, and it has a significantly different source than the low latitude wind, which strongly affects the temperature structure, the alpha wave density, and alpha wave dissipation processes. Thank you.
Questions? I have a question for you. Or go ahead.
I'll ask my question next. Stop, Paulette. Have a mic on that side?
Yeah, and that's very... Yes, absolutely. So that's captured. It actually has a mixture of the two. So that's completely described in the 2015 paper by Rona Oren. It gives actually these charge state calculation as a function of latitude and the source of the solar wind. And so what we found is that there are effects of the magnetic flux tube expansion factors which affect the solar wind speed, but also the speed and the rate at which the solar wind is accelerating along those field lines also affects the charge state composition. So we have a case where the wind is accelerating more slowly and spends more time lowering the corona at higher temperatures, which also adds to the elevated charge state composition. So you're able to get that elevated charge state composition without having to rely on the opening of magnetic field lines. Not that that isn't a significant source of the solar wind, but we can contribute to that effect without having to contribute to that elevated charge state composition on open field lines.
I think we had a question from Craig.
Quick one. Chip, I was really intrigued by your overhead views of the CMEs. We're looking forward to looking down from the pole and seeing CMEs that look more like Jack Gosling's sketches and less like they're seen and on. However, your model, it wasn't clear to me, it's very simplified, and I can't tell how much the simple structure is due to the model or whether we really ought to expect CMEs to look that simple from above.
Oh, I think in this particular case, the model is simpler than I think the paper we published in 2008 of the Halloween event did a very strict, rigorous quantitative comparison with that event. Shows more structure. Particularly, it's a halo event, and over the whole ring of the halo, it's more highly structured. It shows a stronger comparison correlation with the observations. This one is, for reasons I'm not exactly sure, is a little more simplified just in terms of how it came out. It might have been just the effects of the magnetic field or the numerical resolution. I think overall we'd expect it to be a little more highly structured than what's seen here.
Thanks.
Vaughn, thank you again.
And we're moving on to Michael Kirk, who's going to be talking about an assessment of UV polar coronal holes.
All right, thank you very much. Looking up at the slides up there, I noticed that a nice chunk of the slide is missing off the edge. So it's okay on that side? All right, well, just on one screen. So if you're missing an adverb or an adjective, look over on the other screen. All right, so good afternoon. I'm really pleased to talk with you today about some work that I have been participating in for, as Dean pointed out, more than a decade now, which makes me feel a lot older than I think I should be. But it's about measuring polar coronal holes, understanding their evolution over time, and really their impacts into the greater heliosphere. So without getting into too much of the detail, I wanted to take just a minute to talk a little bit about what I'm talking about with a polar coronal hole. Because there's actually a few different definitions that are kind of, they all intersect with each other, but they're slightly different in terms of what a polar coronal hole is. So coronal holes really simultaneously refer to three different phenomenon that are all related with each other, but you kind of interact with them differently. So in one sense, you have these dark patches in EUV or X-ray. So that's the kind of the canonical definition of polar coronal hole. But also, the definition that we were just hearing recently, we've heard kind of in and out of these talks, are about the open magnetic field lines. I'm not talking about the open magnetic field lines, but that's definitely related. The third one is the low emission off the limb of the sun in the iron lines or in eclipse images. Also, again, very much related to these polar coronal holes. I'm not talking about those either. So I'm just talking about the dark patches on the surface of the sun. Just to kind of do a brief overview so we're all on the same page, a little bit of zoology. So there's equatorial holes that exist in mid-latitude regions. Then the northern and southern coronal holes, the polar holes that exist above and below 55 degrees latitude, which is the ones that I'm talking about. Why 55 degrees? Well, there are some dynamics that separate out the equatorial regions from the polar regions at 55 degrees, but that hard number of 55 is more just a choice rather than an actual physical definition that it's exactly 55 degrees. The last definition, last coronal types of coronal holes that are out there are ephemeral coronal holes, which if you're curious about them, ask Dean about, Dean Pesnell. He's done quite a bit of work with a summer student on ephemeral coronal holes and how they evolve. All right. Last little bit of review before plunging into my work is just to go back and talk with you a little bit about what Dean mentioned about the wall effect. So coronal holes, polar holes are especially difficult to see. And most of that has to do with, A, you're looking at the tangential surface of the sun as you look towards the poles. But on top of that, compounding those problems are the issue with emission scale height. So if you have a small emitting scale height in the plasma, then that top graphic, you can see that you have a much more of a high fidelity of that edge, the boundary between the coronal hole and the emitting plasma. If the emitting plasma is down below and the coronal hole's up top. If you have a large scale height in your emitting plasma, like let's just say, I don't know, 211 angstroms, then that edge between the quiet sun and the coronal hole is very obscured. And so you have a very uncertain idea of where that boundary exists from your vantage point. On top of both the oblique viewing angle, the difficulty in the scale height, you also have this differential rotation problem where depending on how big the coronal hole is, that boundary is going to rotate at a different rate. And so you have three different problems that all compound each other, which makes viewing coronal holes, well, viewing anything at the poles, difficult. On top of that, we have a long different timeline of EUV imagers. So starting back in 1996, we started having consistent EIT images of the EUV sun. Then in 2006, we had the stereo missions. 2009 saw Proba 2 swap as well as stereo AIA. And then 2016, we have GoSUVI that are now all taking EUV images of the sun. All of these imagers are slightly different. They image in similar pass bands, but their filters are all slightly different. Their CCDs degrade at different rates. Their characteristics of their light leaks, whether it's in a filter or in the telescope itself, They all have different issues. They have different point spread functions. So all of these different imagers, although they create this nice baseline of 20 years of imaging, they all have very unique aspects to them, which makes it difficult to compare them one against another. So that takes me to the technique that we came up with. So in 2008, 2007, 2008, we came up with an idea of looking at the pole of the sun. So if you look at the pole and just focus in on the area that bisects the quiet sun to the polar hole. So this little transition region right there on the edges of the sun itself, right on the very limb. You can help mitigate some of the effects of that large emitting scale height. It gives you a consistent place on the sun to look, and it stabilizes some of those uncertainties. And so what our idea was is that we just wait for the sun to rotate around and gather up different elements, and we chart out the boundary of the northern polar coronal hole as shown here in the larger diagram. And we can also do the same in the south. So we really just let the sun rotate, and we just gather up measurements of where that edge of that hole is. Oh, hey, now the animation's playing. Okay. So there's a little animated GIF that you can see up there that sort of illustrates that idea of where we're selecting holes, selecting the boundaries of the holes, and then plotting it up. We're charting up, so we're building up that rotation over a full solar rotation itself. So we take those measurements and unwrap them into a Carrington longitude versus sine latitude plot. You can start plotting all of these measurements that you've taken, all these individual points, and you can sort of get a trajectory, a boundary of where these polar holes live. So plotted on here, we have several different missions. We have AIA in 193 and 171. We have SWAP in 174, EIT in 171, and then EUVI both in 171. And you can see that sort of a confetti look to it is that there's definitely a trend there, but they don't really agree with each other between wavelengths, between missions. They all sort of generally say that there is a boundary there, but exactly where that boundary is difficult to pin down. So if we treat each individual mission as a unique measurement, where each mission, each wavelength, is now its own pristine measurement, and then we join them together using confidence intervals. You get something that looks like the blue line that's overlaid on top, where the dark blue line is where the boundary is, and then the confidence interval, the darker blue shaded area is a 90% confidence interval, and the lighter blue, the lighter blue is the 90%, and the darker blue is a 95%, I believe. Anyway, so using them as independent measurements doesn't actually capture the scatter that you visually observe in these missions. It doesn't actually satisfy, even though statistically it's a consistent, self-consistent method, it doesn't actually capture the boundaries of the whole very well. And that's a problem, because these measurements are the best we have right now in understanding where this polar hole is. And so more recently, I went on and did something more interesting, which is using a bootstrap method where you're using dependent measurements on each other to build up statistics using bootstrap methods. That's the magenta line laid over on top yet again, and that better characterizes the noise. But you can see quite quickly that there's a big scatter in where the boundary is. I mean, you can see it with your eyes, but the statistics bear it out that there are locations where it's just inherently uncertain. Okay, so where does that leave us? Well, it leaves us a hole with a boundary and a hole with an uncertainty measurement at every location along the boundary. We take that to the next extreme and actually extrapolate over the entire series of missions that we've been looking at. So from 1996 all the way up until, I think I have data up there till 2016. I had a great hope of having the latest data from all the way up until like yesterday. But I had a hard drive failure a couple months ago, and all that went out the window. So we stepped back in time to an earlier processing. But you can get a sense of the size and the evolution of these things. So on the x-axis, you have time in years. On the y-axis, you have fractional area of the surface area of the sun. The top plot shows the northern coronal hole, and the bottom plot shows the southern polar coronal hole. Laid on top for context are orange bands and the blue band, where it shows the solar maximum and the solar min, the maximum activity and the minimum activity of the solar cycles. And you can quickly see the result that we've known for a while, which is that polar coronal holes peak near solar minimum in terms of their size and their area, and then disappear towards solar maximum. That's been reconfirmed. But what's really interesting is, as we're looking through all of these, not only is there quite a bit of scatter, but there's an interesting little bit of evolution there too. So for reference, I put up an arrow on the top and the bottom that is 10.5 years long in this coordinate frame. So what does 10.5 years get you in the northern hole? Well, the northern hole goes through its entire evolution in 10.5 years. So it goes from forming at the end of solar maximum to disappearing right before solar minimum in 2013, 2014. In the southern hole, you can see also 10.5 years, but the southern hole has taken much longer to evolve. It took a lot longer to coalesce at the beginning, coming out of solar maximum, and then disappeared briefly before coming right back again through the next maximum. So you can see there's a distinct asymmetry there between the way the north evolves and the way the south evolves. All right, so what does this mean for a polar mission, or for looking at polar coronal holes in general? Well, to illustrate this problem that we have in holes and the issues that we are ongoing, I have up here an animation from SPOCA. So SPOCA is an automated detection routine out of I think it's out of Belgium. And you can see here that they're automatically registering and detecting coronal holes, all types, southern, northern, equatorial holes. One thing I want to point out is if you watch carefully, you can see there's an asymmetry in this computer vision routine. This is a state-of-the-art computer vision routine that we're using and that gets piped into the HEC. It's a fantastic routine. But the ascending limb of the sun gets a much better detection threshold than the descending limb. They'll pick up coronal holes right as they rotate onto the disk, and then they'll lose them as they fade off the disk. And so there's this asymmetry in this detection method, which means that there's an asymmetry in some of the physics of how these coronal holes, there's actually a tip to the coronal holes. It's easier to see them one way or another. So it's pretty easy to extrapolate using this idea where we're looking at ecliptic coronal holes, that what are we missing at the poles? If we have this sort of ambiguity with equatorial holes, then the polar holes, my goodness, I mean, there are significant features that we just don't know exist because we just cannot see them. All right, so let's move right into what I want for a polar hole mission requirement. So the animation that you see, I took a synoptic map and I wrapped it around a sphere, and it will start tipping in a minute. So that's kind of what the equivalent of what we've seen with the models is that our data is kind of okay, but it's really not that great, especially when you start looking at the poles. But what I need is 90 degrees. I need to get up to the pole to be able to see those polar boundaries exactly. 45 degrees is not enough. If you get up to a 45-degree latitude, you're just not going to see the full boundary of the polar hole. And so you're going to see one boundary reasonably well, but not the other. EUV imager is absolutely necessary because we have this long 20-year history of EUV imagers observing polar coronal holes. We have to continue that going forward. It needs to be sampled for an appreciable part of the solar cycle. We need to be able to see it over that 10.5-year evolution or 11-year evolution of the hole, from when it coalesces until when it disappears again. Otherwise, we'll be caught with a snapshot somewhere in between, and we'll be always wondering what happens afterwards. But if I had to pick a time, if we were limited and I had to just give you one time that I got a picture of the hole, it would be right after solar maximum, as that polar asymmetry is the most extreme, where you have the hole that has coalesced in one pole and is probably not coalesced in the other. I think that would be the most interesting time for studying the hole in terms of how it forms and how it and where it exists. All right, so just a couple of concluding thoughts, and then I'll take some questions. So polar coronal holes are the longest lived features on the sun. These are coherent features that last for a decade or more, and that's impressive. I have an outstanding question of why? Why this feature can last for a decade when every other feature on the sun gets sheared away, gets advected, gets canceled, gets erupted, yet this coronal hole on the pole sticks around for a decade. That's the question that I have. But our best measurements of polar coronal holes have an absurd amount of uncertainty in them. I've been working at this for a long time, and I've gotten pretty good at sussing out the differences between missions and other issues, but it's still a crazy amount of uncertainty, so a polar mission would clear that up. I would need a 90-degree inclination on the ecliptic for that, full disk EUV imagers, and then have a nominal lifetime of 10 years. So that is my talk. I'd be happy to answer questions about coronal holes, polar coronal holes, or UV imaging in general.
All right, we have time for a couple of questions. Noriaki?
So passbands, you definitely have an EUV passband that's legacy in terms of either 171 or 193. That is necessary. Other than that, I mean, the 211 line is interesting, but it has a large scale height, so something in that area. Resolution, I'm not as picky about that personally. I think that AIA provides way more resolution than I can functionally use, so I actually downsample it. The bigger issue is scattered light. It has to have, the EUV imager has to have very good scattered light capture, because the scattered light will just swamp out the edges, and that's really what I care about. EIT was really rough for scattered light issues. I mean, just the amount of scattered light flux that got into coronal holes was pretty terrible.
We had Chip and then Don.
So in general, I mean, they track well over the 10-year period. They track pretty well. Individually, there's some issues and some variations. I haven't done the study, which I'm kind of curious about, is do specific wavelengths or missions capture one better than the other? And so in kind of vague sweeping terms, I can say yes, they match each other well in terms of as the polar flux increases, the size of the coronal hole increases. There isn't a one-to-one correlation, though, which is curious. We thought there might be a direct correlation between the strength of the polar field and the size of the polar hole, and that's not really the case. They both evolve at the same rates, but there isn't a one-to-one correlation between the flux and the intensity or lack of intensity, or the flux and the size directly.
We had Don.
Yeah, absolutely. Yeah, I'd be really excited about that, because especially in higher energy passbands, you get that asymmetry more. So if you look in X-ray images, for example, you see that asymmetry even more apparent in coronal holes on disk. Yeah.
We have time for one more before we start our panel discussion. Chip?
No, that would be very interesting. I haven't directly compared it to UV emission measures. No, I mean that would be curious. I would be interested to see. Yeah. Yeah. That'd be fantastic. Yeah. Yeah, that's a nice open question as well. How much variation is there? But I'm not sensitive to it either because I wait for the sun to rotate, and so I smooth out that, just by the detection method alone, I smooth out over a lot of those small variations. So I think that would be a nice comparison.
All right, let's thank all of our speakers for a great afternoon session. I see there were a couple more questions, so please take them to one-on-one on the break. I'm going to hand the mic to Sarah.
Yes, and they can also come up during the panel discussion as well as we move forward. So now, Scott, are you going to lead the panel discussion? Let's go ahead and bring our speakers forward, or our panel forward. So basically our invited speakers, I believe that's Leif, Erin, Maria, Lisa, Gordon, Noordine, and Heather, if I've got that right. Come on down.
All seven?
Yeah. Observations, models, primarily about magnetic fields, but also about UV corona velocities. This is your chance to throw a question at any one of our fine speakers this morning. Take your pick. What's it going to be? Should we throw at them the Zerbuchen question yet again? So collectively, if you were to pick scientific low-hanging fruit, each one of you, what would it be from a polar perspective? So not that you're on the spot, and not that we're webcasting this, but I'm going to limit responses to 150 characters so that I can tweet them fast. No, I'm kidding. So the question was, back to the Zerbuchen question, if you were to consider low-hanging fruit, what would your single measurement be, and why? You want me to start at the other end? You want to go? All right, okay.
Well, I think the, right off the bat, if we were talking about first 3 or 4 days, doing a detailed comparison between what my surface flux transport maps show we should expect versus what we actually observed, which shed some interesting insight on maybe how flows might be different or how flux is concentrated into the magnetic network to these kilogauss fields. And so I think that will at least maybe give us some insight on where are the peculiar structures, what do we need to really focus our energies on, where are these differences that really stand out.
So what was the measurement?
The magnetic field at the poles.
Okay. I think the problem isn't just one measurement. I think it's that we need to compare the solar observations and the heliospheric observations. So I actually think that looking at the composition, the elemental abundances, and the charge state ratios, and the heating at the sun, we can probably nail down where this what we think is a boundary layer in the solar observations actually comes from for the coronal hole boundaries.
For me, I would, low-hanging fruit. One snapshot, multi-wavelength of the sun's poles, and also a magnetograph of that as well. you know, the images of Saturn and Jupiter's poles have shown us amazing things that we didn't even expect. And those are just images that tell us something about the fundamental fluid dynamics at the poles is much different than at other latitudes. So even just one of those images could really start our brains thinking. Well, I think we might not know what to expect. I don't know if we knew what to expect at Jupiter's and Saturn's poles either. So, and as I mentioned earlier, even if we find nothing particularly interesting there, that might also tell us something too. Yeah.
Okay. Yeah, if I had to pick one thing for the first few days, it would be local helioseismology near the poles to say something, and also correlation tracking to say something about supergranulation and larger scale flows near the poles. Yeah, to see if there is something different in the supergranulation pattern. Also, if there is something drastically different happening with differential rotation at high latitude, we would see a short observing sequence. Or vortex. I mean, yeah.
Very slow vortex.
So for me, it would be busy interrupting CMEs, and also the 4 pi coverage of magnetic fields. That way, we will have models that are based on near real-time magnetic field measurements. Everybody will buy that.
Yeah, so surprised nobody to hear that I would like a polar magnetogram, possibly a time series, just to see if there's anything surprising or shocking happening at the pole to the field. If there's something in the effects of the granulation or the meridional flow that's producing something unusual. I'm not expecting any polygons or pyramids up there, but even something surprising.
Well, no, not pentagram, magnetogram.
All right.
More or less what the HMI measures now. It also gives us a Dopplergram at the same time. But that should be the highest resolution that we can get. Okay? And for me, the most important thing would be to compare that with what we get from extrapolating what we have now. Okay, because we think now we can sort of assume it is radial, we can map it and verify if that works. Now, if it does work, then the game is over, right? We don't need it anymore, right?
Yep. In principle. Is there any questions that you guys want to pose? Rudy, you got to have one. Sorry, Sarah?
What I was going to say was, we've given you that Zurbuchen question, but it's kind of unfair because you had to do it in 3 days, right? Now, if I take that constraint away, what do you think the lowest hanging fruit is where you're allowed perhaps a longer time?
Well, I think again, absolutely. I have to go back to the magnetic field. I mean, the magnetic field is such a quintessential part of everything that's going on in the sun. And if we could get long-term observations of how the magnetic field changes at the poles, I think that's going to answer many, many questions for us. I mean, it's going to tell us about what the flows look like, how the meridional flow changes at the poles, how the convection changes at the poles. It's going to give us insight to how does the polar field actually build up and produce the seed to the next cycle. I think it answers so many different questions on multiple different spatial scales and temporal scales. So absolutely the magnetic field.
Okay, I think something that's going to take a lot more observations is pulling out the source of this slow latitude trend over the polar coronal holes. And the source of the small fluctuations, are they related to the supergranule network? You have to do detailed comparison with the solar observations and the heliospheric observations, and probably also tie in coronagraphs.
Within the solar interior community, one of the problems that we're having now, as I discussed earlier today, was trying to understand the convective flow speeds in the deep interior. Our simulations are not really matching up with what's being observed in helioseismology, but some of those observations are different as well, depending on the method. So, you know, if we could get some multi-vantage point observations to help us constrain the deep flows and the scales of these flows, like the spatial sizes of them, the ones in the deep interior would really help us out a lot.
If I had to pick one again, I guess it would be solar cycle variations of the torsional oscillations at high latitudes. It's likely to be feasible from the measurement perspective, provide constraints on dynamo models. That would be my one pick.
I would be interested in learning what is happening at the boundaries of coronal holes and whether these are the source of the slow solar wind.
So I of course would like a long-term time series of polar magnetograms just to see how the poles evolve on the cycle timescale. But I think it's also essential to couple those with Dopplergrams just to gauge the large-scale flow patterns beneath the surface, because they're key to understanding how a polar field gets transformed into a new cycle.
Again, it would be very nice, of course, to have long-term data. But suppose we only get one shot at it for days, 4 days, 1 day, then it's got to be the magnetic field. For the long-term thing, I would be happy with one measurement per month or 20 years. So it's between those two poles, so to speak. Magnetic field for me is what we are after, basically.
Billions of dollars per photon captured. Right. Is that the record currently?
So you're saying basically of the two, the short and the long, the short is actually the higher priority, right? You could be glorious, but would be something. Okay. Just
Yeah, in the presentations, there was lots of discussion about the north-south asymmetry and the differences between the north-south. So if you could actually do that on a short time frame but get both north and south, you know, I think those differences, I'd like to hear your thoughts on that.
Anyone want to take that? Yeah.
Well, I think that differences, as already Babcock mentioned and Waldmeyer, it really depends on the active regions at the time and how they develop. So those are really local phenomena. I don't personally think there's anything fundamental in symmetry. It's a local thing.
So I would say it's not fundamentally, theoretically urgent thing to see both poles simultaneously for the same reason. But I think there are compelling practical reasons to do it, because to have a well-constrained coronal or heliospheric model for the global field, you need to know what both poles are doing.
We do see composition differences over the poles, and solar wind property differences, like we observed for Ulysses, but the orbits were really long for Ulysses, so it could be that we observed the poles in a different phase, because the polar coronal holes change size and they move around a bit. And so if you actually did observe both poles simultaneously, you could be learning about the evolution of the poles. And so the two questions can be interlinked.
I think that question is actually an argument for why we need long-term observations of the poles. Rather, I think like Life said, instantaneous look at both of the poles is really going to be very dependent on what the history of the magnetic field emergence has been, and so depending on what phase of the cycle you're at, you might get very different results looking at the two different poles. They may be in sync at that phase. They may be out of sync at that phase. And I think in order to really get an understanding of what the differences are, you need to have that time evolving perspective that makes those differences that you're seeing. So I think that's an argument for why we need long-term sustained observations at the poles.
So we know that the solar cycle reaches maxima or minima in both hemispheres at different times, the poles, right? So from a dynamo perspective, specifically from a flux transport dynamo perspective, learning things about the asymmetries of the magnetism that you see at the poles when you see it reverse, what the flow speeds are like in the meridional circulation there, you can feed those types of things into flux transport dynamos, surface flux transport models, and I think that you could maybe learn some insight from that by seeing what observations have to tell you.
And it's like an upgrade to the realtor's mantra. It's not just location, 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 it's also timing. So careful scheduling of a mission. Burger.
To this point of wanting long-term observations from a mission that goes out over the poles and thinking about how to do that from a spacecraft standpoint, and this is a question, I guess, for Heather. What happened to Ulysses? 3 orbits and out. Was that a fuel issue? Did something else break? It's still out there orbiting, but it's no longer usable. So what?
Yeah, I think it was communications. But a lot of the instruments were still working. I think one of the energetic particle instruments. Oh, power? Okay.
It was an RPG,
oh, okay.
so it's.
Okay.
So it
okay.
Well, didn't have solar panels, or it did, and it did not have solar panels?
A lot of the instruments were still working. So, I mean, we can run particle instruments for a really long time in the field too.
So far, all the sort of the comments about the low-hanging fruit has been about essentially photospheric measurements, or near the photosphere. A few of you pointed out the value of tomography in looking at the corona. I was wondering what low-hanging fruit you guys consider to be out there as far as observations.
Tomography in the corona, or the corona?
Or what the UV images are going to be doing for you.
I think the EUV images, the coronagraph images, are going to be essential to transforming space weather predictions. They're going to give us the information that we need. They're going to give us, the location of the CMEs, the speed of the CMEs, the orientation of the BZ. I mean, critical aspects to space weather. So I think that the coronal images are essential for that component.
The one thing I would like to point out is that BZ is a harder problem. If you are looking down over the sun, you know the field close to the sun. As it travels out to Earth, I mean, BZ and what people talk about for ionospheric purposes is in a coordinate system that depends on the tilt of Earth's dipole, so that's one thing. But en route, there's enough compression that you get, I think, between like a 10 and 20% change, an enhancement in the field strength, which will affect your BZ significantly. So that's actually a little more difficult, but I think somebody else might have something on that question too.
Yeah, so I'd be hunting for sympathetic eruptions. I don't think we know nearly enough about what causes flares and CMEs, and I think the magnetic context of the active regions has a lot to do with it, and we need an extended field of view to study that further.
Listening to what people say here, sort of get the feeling that, well, that's all things that we know about. There's no dramatic discovery that nobody was thinking about, right? So what I would really want is that thing that nobody knows about.
I would actually argue that in the fact that I think that having those coronal images will help disentangle some of the discrepancies we're seeing. For instance, when we put our synchronic maps into coronal models, they're not accurately estimating the IMF. And so I think having those coronal observations will help us better disentangle where are these discrepancies coming in. Is it coming from our boundary condition? Do we have that off? Is there some kind of physics that's going on that we're missing? How do we get that link between the magnetic field measurements and to the coronal models to more accurately represent what's actually occurring in the sun and the heliosphere?
Dan, did that adequately address your point, Neil? Did you have something else to follow up with, or?
I want to ask you guys a very pragmatic question. As you'll hear tomorrow, one of the lessons we've learned working on Solar Orbiter is that these exotic orbits introduce some challenges in the form of telemetry and data storage. And you have to make some really difficult compromises because you can take as much data as you want, but you can't keep it all on board. You can't talk to the spacecraft all the time necessarily. And you can't talk to it very fast. So maybe you have great ideas for what you can observe if you can just observe anything you want, but some other instrument needs the telemetry. So let's say we have to prioritize the kind of observations that we're going to make to fit into a relatively small box of data we're going to get back. What's the most important observation?
Oh, the money question. Oh, Noor jumped right at it.
I think we definitely need magnetic fields, but we have to be thinking of probably making inversions on board, that we don't have to downlink the Stokes data. We'd have to downlink already magnetic fields. That's one. We need white light images and coronagraphs and heliospheric imagers. We need spectroscopy. That is really important because what we learned from SOHO about what is going on in the base of the corona is really important. But unfortunately, we cannot continue it because NASA does not select any mission that is doing spectroscopy, and it's really important.
Many things in the chromosphere and lower corona are optically thin, which when we're looking down through them, we don't see anything. So that will be a problem, I think. What doesn't suffer from that is observations of the photosphere. There we have photons, lots of photons. So, for example, one of the things that will be very hard to observe is the spicule forest from above. What does that look like? It will be more or less invisible because imagine you have those spikes sticking up. We look at them from the side, we see a lot of them, but if we have to look at them from above, it may be very hard to see. So that limits to my opinion a lot of the things that we would like to get. So I will just go back to what I said the very first time. The magnetic field, that's it.
But I think the point that Dan was trying to make is that you're in a profoundly data-starved environment. And you've got to pick one kid. I've got 5 kids.
But you don't necessarily have to pick
which kid do I need to preserve or just preserve from time to time?
You don't have to necessarily pick one kid, but you can only maybe look at one set of observations from one kid at a time. So, with Solar Orbiter, we can do a bunch of different things, but you got to make trades. You look at the magnetic field when it's the most important. you look at the EUV when it's most important, but how do you strike that balance? You can put all the instruments you want on the platform, you just can't get all the data back.
Aaron?
Yeah, we've thought about this kind of question a fair bit in the context of thinking about helioseismology with Phi on Solar Orbiter. And I really don't think that it's a matter of choosing one thing. And another resource that you didn't mention is processing power. And it may be that there are some things that could be done on board that would save enormous amounts of telemetry, but give us things that would still be very interesting from the science point of view. So an example would be, could you take high resolution image pairs every so often, say image pairs separated by a minute or 45 seconds at high resolution, do the correlation tracking on board, reduce the resolution on that and send it down. Another example would be, maybe you take full disk images, bin them down to something like, LOI resolution on SOHO, and you send down a 10 pixel by 10 pixel image. And this would be fine for some kinds of tomography of the deep solar interior. You don't care about L of 200 if you want to go through the deep sun. So I guess I would hesitate to frame it only as trade-offs, but I think there's room for creativity in coming up with a program.
Yeah, I guess that's the point, though. That's the trade you're making. You don't get all the data. You can not massage everything out of it, but you make some choices about what you can do on board to get the best return on the observations that you're able to make.
I just have one short comment. I think if you think about a lot of smaller spacecraft, you could consider a relay system.
Has anybody ever done that before?
I don't know.
Planetary
Oh, the
people are
questions are lining
implementing a
up.
relay.
I think we're in an emerging exploratory space when it comes to satellites, and we do have to get creative with how we plan these missions. How can we set up multiple satellites that maybe can do relays? How can we do some of the processing on board? But I think there are novel solutions out there that don't necessarily mean that you have to, reduce all of your data to the bare minimum. I think it is an important question, but I think there's also important questions that need to be asked in terms of how can we use this new technology that's available to us to make better choices to increase the volume that we are able to bring back.
So I have a couple of immediate follow-ons. Nariak is a question. Is it immediate follow-on or is it a separate question? Okay, we'll get back to that in a sec. Craig, do you have an?
It's all the way.
Carol? Oh, no. Don?
technology definition. Mission was so technology dependent that you really needed to have engineers working hand in hand with scientists. And that's a similar concept for this kind of a mission. The thing I think we want to do going forward, for demo things that we really want. Solar and Heliosphere. Every program, they have a New Frontiers program. They have tech and fusion for every element of those. And heliophysics doesn't have that, but we need that.
It's a really good point, Don, and it's a shame that the optical or the laser comm guy that was going to come couldn't make it. So right. So Craig, Nariaki, Carol.
All right, so getting away from program design and mission design back to science. Let's see, I heard a lot of discussion about the global dynamo and things we could find out about it from looking at one or both poles. I didn't hear a lot of discussion of the local dynamo, which is something that in a past life I was really interested in, still am. Dr. Shriver also is in that situation. What can we learn about the small scale dynamo from looking at the sun over the poles? Any of you folks thought about that? I know I have.
Well, I think Maria mentioned it in her talk about looking for the local dynamo, and I think that may be one explanation for why we're seeing those kilogauss fields in Hinode, where we're not really necessarily seeing them in our surface flux transport models. And I think absolutely that's a great exploratory space there. I don't know, Maria, you might have more to add.
I don't have a whole lot more to add because I haven't done and studied a whole lot about local dynamos myself. But I mean, I do have a feeling, and I think we do also from our simulations, that there's a little bit of a different change in the convection at these high latitudes, and the convection is what generates these magnetic fields, especially on local dynamo scales. And once you get outside of the tangent cylinder on the sun, you have in the tangent cylinder creating these banana cells near the equator, and then above that you have these more isotropic cells nearer the pole. And I think some things are happening up there that might create, lend to these local polar dynamos or something different with the magnetic field generation near the poles that would link into a global dynamo as well. So these are speculations and thoughts that I might have. I don't have any good science, good backup for it, I guess, at the moment. Anybody else?
Yeah, we have to make up our mind. We want to solve one big problem, and what should it be? Or 10 small ones that nobody cares about. We also need to think about mesmerizing the public, make it exciting for them. Okay? And some of the things that have been brought forward today are not really exciting for the public. So that is a big part of deciding what to do. But after all, who's paying for this? Right?
You mean like a gobsmacking image from Juno looking at Jupiter's poles, for example?
And maybe
far less a sequence of them?
Yeah, maybe even involving the public in citizen science.
Citizen science, the gobsmack factor. It's just to find a new criteria for proposals. Sorry, Bob? Right? Ultimately. Also, when it comes to Congress, too. Nariaki had a question. Then Carol.
Yeah. I think that the nature of going to the poles and being able to see the sun from this entirely different vantage point, I mean, is going to speak to that just innately. I mean, if we can see this spiral structure, I think spirals just are where we are naturally attracted to spirals, and we see them all over in nature. And I think, you know, being able to see some of that spiraling features, being able to observe the magnetic field spiraling in, the coronal structure spiraling around, I think you know, that's absolutely going to be a good place to engage the public.
I have one comment. As being a particle person and having lots of spectrograms and line plots, we are at a disadvantage. However, in this situation, a lot of the science that really needs to be done is connecting a lot of the imagery work with the particle work. And the one advantage particles does have is that we look a lot more towards the actual getting closer to what will cause consequences at Earth. So we have a lot more practical, I think, like applications that we can do, but we don't have the glamorous pictures without coordinating with the imagers.
There is one more thing we have to keep in mind is how this future mission will fit with respect to existing ones and other plans also from other countries. We have Solar Orbiter that is going above the poles. Probably people will say, okay, wait to see what Solar Orbiter is going to do. There are rumors that the Chinese also are planning a polar mission as well. So we have to be really to come up with a very attractive plan.
If the Chinese are considering a solar polar mission, that would certainly accelerate a US one.
We can use that.
Okay, Nariaki.
I spoke with a Chinese person, and he says that China won't do a polar mission because it won't produce Nobel Prize. That's what he said. Anyway, I have a question about BZ. Some of you talked about using polar mission to better evaluate BZ in the context of space weather. Is that really true? Because we're not proposing corner magnetograph, right? And what is important is a corner magnetic field. You okay? But even yeah.
Hey, right now the sky's the limit, right? We haven't talked about our instrument payload. So if you could put a chronal polarimeter on board, check out my poster over here.
Okay.
We did the calculation. And Yuhong has done a paper that's just been published, which talks about if you had a Cosmo, which is a 1.5 meter telescope observing circular polarization, what it would observe. So I took that calculation, but did it from the pole, and first asked if you had a 1.5 meter telescope at the pole, what would you observe? What would your photon noise? Could you see BZ? And then I just made it smaller and smaller, and I got down to 10 centimeters. And you can see the sign and the magnitude of the BZ of the CME as it goes out. So yes, for space weather purposes, you could measure it.
That's nice. But
out just in the first three solar radii. So you are not seeing what you're talking about. So you need to see also the outer chronographs and heliospheric imagers to see how it changes. But in terms of getting the source and when it leaves the sun, yes, you could observe it.
But heliospheric imagers don't observe magnetic field. That's density.
No, but this does. This is BZ. This is circular polarization, line of sight magnetic field strength.
No. Heliospheric imager outside 3 solar radius.
Right, but you have an input model of your magnetic field as it leaves the sun, and then you have to evolve your model taking into consideration what you observe in the heliosphere, in the heliospheric imagers about how it piles up, how it changes, deflects, etc.
I'll look at your poster.
Okay, yeah, I think that her last point is true, that if you understand how much a compression is happening within root, you could integrate models and all of the data together to get a pretty good estimate of what's going to happen to BZ.
Any other takers before Carol? Okay, so BZ is plausible, at least out to 3 arsuns, which then you're feeding a model. So, Carol.
A rather broad question. You've brought up Thomas Zurbuchen's question. I'd like to think back of what Dick Fisher always said. So what, who cares? So if you're asking the question, what's the most important measurement to make, you can give it in 2 different ways. There's your scientific preference, and there's the political strategic preference. You're not going to get $500 million or $1 billion by saying, I'd like to do this a little better, or maybe I'll be surprised. So come up with the one-liner that will sell this mission. I can come up with, I'm trying to hear such lines. I heard two, and I probably missed your favorite. One is, there's this huge wedge of the solar dynamo that we've never had access to. But if we go to do seismology of the polar depth field flows, we have access. The second is, we've never had a 4 pi boundary condition to the entire heliosphere. This mission can do this, or whatever mission you come up with. What are other lines you come up with? One-liner to sell it.
Okay, and this is not a one-liner that takes the whole time to go from the ground to the top of the Empire State, right?
Well, mine
110
obviously is the 4 pi, and you know, that's my biggest selling point is wanting that 4 pi perspective.
I think another big one is the CMEs, because you can have a view looking down on them. That, and then the fact that the ultimate solar wind conditions you observe are based partially on source and partially what happens en route, and the coronal holes can extend down, and those are very geoeffective.
I also agree with the 4 pi selling point. But then another point that I brought up in my talk that I forgot about a little bit is that what we learn about our sun at all latitudes, we can also apply to other stars at all latitudes as well. So I think that will also help us sell our work to the rest of stellar astro.
Good luck.
I'm sorry, I had one more. I guess the other really big selling point is that we are at the dawn of a revolution in space age, and we're getting ready to start exploring outside of our Earth, our little Earth perspective. And as we do that, we really do need to understand the full heliosphere. So really selling the point that we are extending our exploratory space, we're moving out into new frontiers, and to be able to navigate these new frontiers, we really need to be able to see the sun as a whole.
Characterize our star to help with others.
Yes, yes, yes.
There is a good slogan, it has been used already. It is that of STO. All the sun, all the time.
Half the sun all the time.
A third of the sun all of the time. Right, I had Dean. Yeah, has anyone, Carol, are you okay with that? Did you get enough buzz lines? Right?
Then the other questions.
Yes, indeed.
So the first thing is a comment. So I've been through mission designs for 20 years. Stop telling the other people they can't do their stuff. Okay? You need to come up with 10, 12 instruments that'll address these science topics. This is not our place to go through and say it doesn't fit the budget. Okay, it's better to come up with 10 sound ideas and let the science technology definition team go through and figure out how to manage that than it is to start pointing around and saying, no, we can't do that. We don't need to prioritize yet. We need to come up with good things, good science that can be done and impossible instruments. The second thing is, what's the money shot? So Michael put his little animation up. That was a limb synoptic map from AIA. I couldn't tell what wavelength it was. It looked like crap. Okay? And why did he do that? He did that so he could wrap it around on a sphere and it rotate to an arbitrary angle so he could see what the polar perspective would look like. But guess what? Science on a sphere doesn't work with the sun. The sun is inherently a three-dimensional object. And when you project it onto a sphere is still a two-dimensional object, no matter what other people say. And you can't see all that stuff that comes out from the sun. And so what we really want to do is take one of those, I mean, we used to play with these all the time at Goddard. They're actually kind of fun. You wrap synoptic maps around and you kind of look at the different viewpoints. What we really want is to be able to look down and see what the sun does naturally and see everything coming off of the sun and have that science on a sphere that really looks like the sun actually looks. So, but let's not limit ourselves. I've been through too many of these things where people started shooting at each other. That's not our place. And one last point, there is no SDO for this mission. When you guys take off, SDO we say has another 10 years. It's a nice easy number for us to remember. But SDO will probably be done and retired before this goes. What's your other point? Who's the other, you're going to be out there looping around the solar system. Who's the other point that's going to be providing the more continual coverage at this time? I know GOES will be doing the EUV images, but where's the magnetograph? Where's the Dopplergrams? You're going back to ground-based, and we know that the HMI is better in many ways. Yeah, it has problems, but that's another thing that you have to start thinking. Who's your accompanying stuff? Who's going to help you?
A constellation of satellites, and so a lot of the missions are talking about using multiple vantage points. So, for instance, Tom's talking about these 4 different vantage points. So that gives you pretty much a 360-degree view of the sun, even if you don't have the Earth line of sight.
They're all 4 data stars. What you really need is something that's watching the sun in a continuous monitoring sense, like GOES will be in the EUV, but for the magnetograms and Dopplergrams, so you can add on to that. If you don't have that in space, then you're in a data-starved environment, and it's a much more difficult set of measurements now. You don't have the thing to tie those 4 together, as they're looking all over the place. Pardon? You're not even guaranteed that anymore.
Ian, your first point was good. Your second point, that's not our purview here on this meeting to second guess what other missions are going to be flying at some point in the future. But I think trying to look at the priorities, or no, not the priorities. Look at the scientific questions, and then what are the requirements to answer those questions. I think that's the most useful thing that will come out of this workshop.
Yeah, but also following up before life is, do we need a stable reference point at wherever, right, in order to add context to all of this? I mean, or do we just assume that from a strategic standpoint, NASA's going to provide that? So, Life, you had a point.
Yeah, I think if that, thinking about 10 or 12 different things we might want to do, just means we have lost the focus. So I disagree with Dean on that point. And a thing that is sort of popular these days is the idea of multi-messenger. We can sort of fold that into what we try to do. That will at least agitate some people. Right?
Well, I will tell you that as someone who maintains a ground-based synoptic type observatory, it's a huge challenge to keep it funded, especially at a viable level. And I'm sure my colleagues at NSO say exactly the same about Gong. The only reason that Gong's being supported right now in large part is because the operational agencies have taken a strong interest. And so at some level, that stable reference point, whether it's from the ground or from space, is required. It should be a foundational thing going into all of this. But then we need to work together as a community to enforce that. We all want to do solar polar science. All of us. We've all got our own little niche thing that could or could not be addressed by a solar polar mission. But that baseline reference, we require. I mean, it is a zeroth level thing that I think we're all basing our assumptions on talking about this, that stable thing will always be there. But in the practical reality of how funding is allocated, even if we're talking about innovative instruments that measure the sun's coronal magnetic field, right? Trying to push that through the national agencies is a freaking huge challenge. They're not interested, right? They'd rather spend billions of dollars on a very large facility to look at something 32 light years away than something to look at our star. I can't hedge on that. But it's very important. But as a community, strategically, we need to be thinking about supporting those long-lived facilities. And DECUS is a long-lived facility, right? It's a 50-year facility. But it can't really answer that global question, that the global itch that we're all going to have. So I think Chip's been waiting for an extraordinarily long time. And I mean, he's almost passing out at the back of the room.
Busy over here. So one of the things I was going to point out is that there's a real opportunity for looking at the sources of coronal heating. Because point out that the coronal magnetic field in the polar regions is significantly different. There's a lot more unipolar flux, so there's going to be a lot less magnetic reconnection, less nanoflares going on. And so that's going to be significantly different. You've got a large area of more uniform magnetic field. You're going to have more uniform heating. You can kind of tease out what the individual processes are. You have the combination of remote observations, extreme ultraviolet, it's going to give you the temperature. You've got the magnetic field. And then you can combine that with in situ observations of the charge state composition, which tells you about the temperature structure. And then you've got maybe the in situ observations of Alfvén wave energy dissipation processes. I think there's a real opportunity to say something about coronal heating that you couldn't do from low latitude, where you're in the slow solar wind and everything is just a mess. It's extremely intermittent. A lot of different things are going on, so I think that's a really unique opportunity.
Anyone want to take that? Because I think we're back to our coronal imaging spectral polarimeter again.
So, I totally agree with you, but I hate to say this, that if we go with that argument, people will jump at you saying right away, probe is going to do that. If probe doesn't do it, no other mission will do it. They will say that. As a scientist, I agree with you completely. Talk to the whoever, they will give you this argument.
I mean, you could obviously wait for the results to come in from Solar Probe and see what the limitations are and then build upon that. I mean, sir, anytime there's a great mission like that, it usually creates more questions than it answers. So you could build upon those unanswered questions and say, we could go to this area and answer those questions.
The path forward, yes, I totally agree.
Okay.
I think the more connections we can have to space weather, that's an advantage that we have. Because for years, I've been on planes and try to tell people what I do, and they're like, well, what's the point of that? I get that a lot. But yet at the same time, these are the same people that think these these astronomy pictures and astrophysics pictures are like really cool. But the thing is that our stuff is actually practical. And I think the more that we push that, the better. I mean, Rich Binky pushed space weather back in the early 1990s, and that went pretty well. And then there's been another resurgence of pushing space weather, and it's actually increased our budget.
Therein lies the problem, practicality. We have to be more abstract, I guess. No, I'm kidding.
Well,
of course.
And I think you can make those studies sexy. I think, you show somebody the Cinderella loop, you show somebody a CME and put a scale model of the Earth next to it, and that's going to immediately pique their attention. So there are ways to make those kinds of science sexy to the public and still get at the features that you need to do the science.
So, if I can intervene, I think Aaron brought up a good point, and Noor brought up a big point. Solar Orbiter, we talked about probe. Probe can do that. Orbiter is going to get up to about 35 degrees latitude, right? Is that correct? But it's going to take 15,000 years to get there. No, it's about 7 or 8, I think. 7 years. So what's going to be asked is, what can we do here that Orbiter won't be able to do? I mean, for me, I saw it in a few slides earlier, and I'll show this. I'll put it in my slides for tomorrow. I'll put it in a lovely colloquial. What the hell's going on at 55 degrees? Why? What's going on between that tangent cylinder and that polar region that is so regular? It's so amazingly regular. Makes my brain kind of boil. I mean, it's not getting to the so what, and it's more of a scientific version of that than the bigger so what and who cares. Is that important? Is it a red herring? I'm just making a statement, but what can a legitimate mission to above 60 degrees latitude answer the orbiter can't?
Well, I think orbiter is limited in, correct me if I'm wrong, the duration that it's going to be making the observations. Isn't it only going to be short durations?
I'll talk about that a little bit tomorrow, but yeah, Solar Orbiter has 10 days. There'll be a few days over 32.
Yeah.
I mean, in 2029, they will do their last VGA to get up to 32 or 34 degrees. Up until then, they'll be at about 25 degrees.
Right.
They have about 10 days when they pop up to that latitude. But the biggest restriction is actually, to a large degree, also their telemetry.
No, 10 days of observation. And so I think that answers the question right there, because a lot of the things that we've talked about being really interesting to study are longer lived. I mean, if you want to measure the large scale flows, you need lots of observations over long time periods. If you want to look at the convection up there, you need lots of observations on longer time periods. If you want to study features over the course of their whole lifetime, you're going to need consistent observation for months at a time, and Solar Orbiter just doesn't offer that. And so I think the longevity of a dedicated polar mission is what's crucial here.
Tweak that just a tiny bit.
I agree, but when we started out, we did the Zurbuchen question, where the duration wasn't the issue. So if you take the duration out of there and you really kind of focus on something like the angle, how many of those things that we went down the line you said were the low-hanging fruit is orbiter going to do?
Been taking copious notes.
Well, I mean, I guess, you know, it's going to give us a snapshot, but I feel like, you know, a snapshot only gives you a small piece of the puzzle, and I think to really get to a full understanding of these different processes, we need that time evolution.
No, I agree, but I'm asking, like, for example, you said something about.
Sure.
Do you think you could see that?
I'm not sure the details of the instrumentation on there. How well, you know, what's the resolution of the magnet?
And we don't have to answer.
So I'm not positive. I would have to look at the details a little bit more. I don't know. Do any of you have?
Well, for particles, we actually need to be simultaneously at the different latitudes, really high and mid, to answer like the boundary questions and the interior versus the boundary and how the extensions. But you would like to be at the pole too, because we won't know what's happening at the polar latitude if we're not all the way up at the pole.
So for various reasons, we think the polar fields are almost radial, and it's much easier to pick up weak flux in the line of sight component than the transverse component. So how much flux are we missing because we're viewing the poles from the ecliptic plane? If we could see most of the vector along the line of sight, we might pick up a lot more polar flux.
And the last point?
And the various MSD models that people make of the corona and the interplanetary space, they always come up with facts with magnetic fields that are too small, by facts of 2 or 3. So as Gordon says, we're missing. There's some flux that we don't see, right? Now there's a saying in solar physics. I've been in this field 50 years or something, and it goes something like this. What is really interesting is just below the level of resolution, and that holds true no matter what that level is. Okay, it's always been that way. If we can just get one more arc second, or we can just get one level down, everything will be crystal clear, and it has never been.
It's never been followed through. So, do you want to answer that?
I think that goes back to the question of, it's not a matter of whether or not will Orbiter surprise us. It's a question of how they will surprise us. And I expect that when Orbiter gets up to those latitudes, yes, we may find some of these answers that we're looking for, but we might find more questions as well.
Yep, good point. And so with that, you've all been very generous with your questions. I want to thank the panelists who've been generous with their time, having been relatively unprepared for that. I think they did very well. So we're going to break for not very long, 12 minutes. We'll get back here at 4 o'clock. Okay, thanks very much.